Well, the first thing I have to tell you is that you probably have some picture in your head about magnets. You know magnets, of course. Little things on your refrigerator holding up your shopping list, your kids' drawings, that pizza coupon you keep meaning to use. You've held two magnets and felt them snap together through empty air. Or you felt them push apart, that strange invisible resistance. No wires, no contact, just this force reaching through space. And if you've thought about it at all, you probably figured, well, that's just how magnets work. It's magnetism. That's the explanation. But here's the thing. Ask the simple question. Why? Why does this happen? And you'll find something remarkable. The answer is not simple at all. In fact, the answer is this. Classical physics cannot explain magnetism at all. There is actually a theorem proved about 100 years ago called the Bohr-van Leeuwen theorem that says if you use only classical physics, ordinary Newton's laws, and classical electromagnetism, you get a very clear prediction. All materials should be non-magnetic. Every single one. Zero magnetism anywhere in the universe. And yet, here you are holding a magnet to your refrigerator. Think about that. The most ordinary object in your kitchen is proof that the universe runs on quantum rules. Let me tell you what magnetism is not, because this is where people get confused. It's not primarily about electrons orbiting the nucleus. That contributes a tiny bit, but it's not the main story. And it's not about moving charges creating magnetic fields, though that happens too. That's electromagnetism, which is related but different. No, the reason magnets work, the reason your refrigerator magnet sticks, is something called electron spin. And this is where it gets strange. Every electron has a property called spin. It creates a tiny magnetic field, like a miniature bar magnet. Now, you hear the word spin, and you probably picture the electron rotating, right? Like a little planet spinning on its axis. That's what I pictured when I first heard about it. But no, no, no. Spin is not actually spinning. The electron is not rotating. This is a purely quantum mechanical property with no classical analogy whatsoever. The electron just has this property, the way it has charge. It's intrinsic, built in. And this spin can only point in one of two directions, up or down, nothing in between, not spinning faster or slower, not tilted at an angle, just up or down. You see, this is already telling you that something strange is happening. Classical physics doesn't have properties. There can only be one value or another with nothing in between. That's quantum mechanics showing its face. Now, here is the question. If every electron is a tiny magnet, why isn't everything magnetic? You're made of electrons, billions and billions of them. Why don't you stick to refrigerators? Why doesn't your coffee cup stick to your laptop? The answer is beautiful. Most of the time, electrons pair up. There's a principle in quantum mechanics called the Pauli exclusion principle. It says two electrons cannot be in the same quantum state. They have to differ in some way. And one of the ways they can differ is spin. So electrons pair up, one spin down. And when they do that, their tiny magnetic fields point in opposite directions. They cancel out perfectly. No net magnetic moment. In most atoms, in most materials, every electron has a partner with opposite spin. Copper, gold, aluminum, plastic, wood, glass, your hand. All the electrons are paired up. All the tiny magnets cancel out. Result, no magnetism. But then there are these special materials, iron, cobalt, nickel. And here's where quantum mechanics does something truly remarkable. In these metals, there are unpaired electrons, electrons without partners. Their spins don't cancel out. And now something very interesting happens. Something called the exchange interaction. Let me tell you what this is. You have two atoms sitting next to each other, both with unpaired electrons. Those electrons interact. They feel each other's presence. And according to quantum mechanics, according to the Pauli exclusion principle, those two electrons cannot occupy the same state. Now, in most materials, the way the electrons solve this problem is by pointing their spins in opposite directions. Anti-parallel. That keeps them in different states. Fine, no magnetism. But in iron, in cobalt, in nickel, something different happens. The electrons can lower their total energy by aligning their spins parallel, same direction. Now, this seems strange. You'd think parallel spins would mean the same state, which violates the Pauli principle. But no. The spatial part of their wave function is different when the spins are parallel and the total energy works out to be lower. The math is complicated, but the result is clear. The electrons want to point the same way. And when they do, magic happens. Not really magic, physics, but it feels like magic. One electron aligns with its neighbor. That neighbor aligns with its neighbor. That one aligns with the next. It's a cascade, a chain reaction of alignment. Billions upon billions of tiny quantum magnets, all pointing the same direction. And their microscopic magnetic fields add up. They add up to create a microscopic magnetic field. A field you can feel, a force strong enough to hold paper to a refrigerator door. Think about that. The force you feel when you push two magnets together, that resistance, is the Pauli exclusion principle operating at the scale of your hand. It's quantum mechanics made tangible. Now, here's something that seems like it shouldn't work, but does. Even in a piece of iron, not all the electrons point the same way throughout the whole piece. If they did, every piece of iron would be a magnet. But that's not what you see. You can have a nail made of iron, and it's not magnetic. You have to magnetize it first. What's going on? The answer is domains. Inside the iron, there are regions called magnetic domains, where all the spins are aligned. Inside each domain, you've got billions of electrons all pointing the same direction. But the domains themselves point in different directions. One domain points north. The next domain points east. Another points down. All these domains with different orientations and their magnetic fields cancel out. The nail as a whole has no net magnetic field. It's not magnetic. But now you bring a magnet close to that nail, or you put the nail in a strong magnetic field. And something happens. The domains that happen to be aligned with the external field, they grow. The boundaries between domains move. Domains aligned with the field get bigger. Domains pointing the wrong way get smaller. Eventually, if the field is strong enough, all the domains align. The whole nail becomes one big domain. Now the nail is magnetized. Now it's a magnet. And it stays that way even after you take the external field away. The domains stay aligned. We call this a permanent magnet. You see, the exchange interaction is strong enough that once the domains are aligned, they want to stay aligned. It takes energy to flip them back, so the magnetization persists. That's why you can make a magnet by stroking a nail with another magnet. You're literally dragging the domains into alignment. But there's a limit. Heat a magnet enough, and the magnetism disappears. There's a temperature, called the Curie temperature, where thermal energy overcomes the exchange interaction. The atoms are jiggling around so violently that the spins can't stay aligned anymore. They randomize, the magnetism vanishes. For iron, this happens at 770 degrees Celsius. Heat an iron magnet past that temperature and it stops being magnetic. Cool it back down and you can magnetize it again. But the magnetism doesn't just come back on its own. You have to realign the domains. Pierre Curie figured this out in 1895. He was measuring the magnetic properties of materials at different temperatures and found this sharp transition. Above a certain temperature, magnetism gone. Below it, magnetism possible. It's a phase transition like water freezing or boiling. And it's another signature of quantum mechanics. Classical physics doesn't predict anything like this. Now here's where it gets really interesting. Why only iron, cobalt, and nickel? Why don't other metals do this? Aluminum is a metal. Copper is a metal. Gold, silver, platinum, none of them are magnetic. What makes iron special? The answer is the exchange interaction. In iron, the exchange interaction is about 1,000 times stronger than the ordinary magnetic dipole interaction. That's the interaction between two little bar magnets. The exchange interaction is not about magnets attracting or repelling. It's a quantum mechanical effect that has no classical analog. It arises from the Pauli exclusion principle and the spatial properties of the electron wave functions. And in iron, this interaction favors parallel alignment of spins. But in most other metals, the exchange interaction favors antiparallel alignment, or is just too weak to matter. In copper, the exchange interaction says the electrons should point opposite directions, so they do, no net magnetism. In aluminum, the exchange interaction is weak and complicated, and thermal energy at room temperature is enough to randomize everything, no magnetism. Only in a handful of elements, iron, cobalt, nickel, and a few others, does the exchange interaction strongly favor parallel spins at room temperature. That's why magnets are rare. And this, I think, is beautiful. Your refrigerator magnet is quantum mechanics made visible. The stickiness you feel, the force pulling the magnet to the metal door, is electrons obeying the Pauli exclusion principle. It's wave functions overlapping. It's quantum states being forced to be different. And it's happening in every magnet you've ever touched. Let me tell you what Richard Feynman said about this, because I think he put it well. In his lectures on physics, he talked about the exchange interaction, this quantum mechanical force with no classical explanation. And he said it's one of the most remarkable things in nature, a force responsible for something children play with, something so ordinary we take it completely for granted, and yet it has no explanation in classical physics. None. You cannot derive it from Newton's laws. You cannot derive it from classical electromagnetism. You need quantum mechanics. You need the Pauli principle. You need electron spin, which is a purely quantum concept. Think about what this means. Every time you stick a magnet to your refrigerator, you are seeing proof that classical physics is incomplete. You are seeing proof that the universe, at its core, runs on quantum rules. The magnet is evidence. Direct, tangible evidence that you can hold in your hand. Now, there's more to this story. The exchange interaction doesn't just make ferromagnets, materials like iron that have strong permanent magnetism. It also makes antiferromagnets and ferrimagnets and a whole zoo of magnetic behaviors. In antiferromagnets, the exchange interaction favors antiparallel alignment, but in an ordered way. You get neighboring spins pointing up, down in a regular pattern. No net magnetism, but a definite quantum mechanical order. Manganese oxide is like this, chromium is like this, and then there are materials where quantum mechanics creates even stranger behaviors. Spin glasses, where the spins freeze into random orientations. Spin liquids, where the spins keep fluctuating even at absolute zero. Topological magnets, where the magnetic structure twists in ways that can't be undone without cutting the material. All of these are quantum mechanics playing out in the magnetic properties of matter. But the simplest case, the most familiar case, is the ferromagnet, iron, the magnet on your refrigerator. And the explanation is quantum mechanics. Pure quantum mechanics. You know, there's something profound about this. Humans have known about magnets for thousands of years. The ancient Greeks knew about lodestones, naturally magnetic rocks that would attract iron. The Chinese used magnetic compasses for navigation as early as the 2nd century. For millennia, people used magnets without having any idea why they worked. They just did. It was a mystery, a force that acts at a distance, a force with no visible cause. And even after scientists started studying magnetism seriously, even after they discovered that electric currents create magnetic fields, even after James Clerk Maxwell wrote down the equations of electromagnetism in the 1860s, the fundamental question remained. Why are some materials magnetic and others not? Classical electromagnetism could describe how magnetic fields behave, but it couldn't explain why iron is magnetic and copper is not. The answer came from quantum mechanics. In the 1920s and 30s, physicists worked out the quantum theory of the atom. They discovered electron spin. They figured out the Pauli exclusion principle. And suddenly, magnetism made sense. It wasn't a new force. It was a consequence of quantum mechanics. The exchange interaction, the alignment of electron spins, the formation of magnetic domains, all of it followed from the quantum rules. And the Bohr-van Leeuwen theorem, proved in 1911 by Niels Bohr and later by Hendrika van Leeuwen, made this absolutely clear. If you take classical physics, classical statistical mechanics, classical electromagnetism, and you calculate what should happen, you find that all materials should have zero magnetism. Zero. The classical prediction is completely wrong. The fact that magnets exist is proof that classical physics is not the whole story. Now, here is something practical. Magnetism is everywhere in modern technology. Your computer's hard drive stores information using tiny magnetic domains. Each bit of data is a domain pointing up or down. Your credit card has a magnetic stripe. The strip on your subway card, the motors in your car, your washing machine, your fan, all of them use magnets. Magnetic resonance imaging, MRI machines in hospitals, use incredibly strong magnetic fields to see inside your body. Particle accelerators use magnets to steer beams of particles. The electrical grid uses transformers, which are just coils of wire wrapped around magnetic cores. Magnetism is one of the fundamental technologies of modern civilization, and all of it depends on quantum mechanics, depends on electron spin, depends on the Pauli exclusion principle, depends on the exchange interaction. If the universe ran on classical rules, none of this would work. There would be no magnets, no magnetic storage, no MRI machines, no electric motors. The technological world would look completely different. But the universe doesn't run on classical rules, it runs on quantum rules. And magnets are the proof, sitting right there on your refrigerator. You see, this is how physics is. You start with something familiar, something ordinary, something you've seen 1,000 times. A magnet holding a piece of paper. And you ask, why? Why does this work? And the answer takes you down into the quantum world, into the realm of electron spins and wave functions and exchange interactions, into a place where classical intuition fails, where particles aren't little billiard balls, where properties can only take certain values, where the whole idea of a thing being in one place with one state stops making sense. And yet, from that strange quantum foundation, you get the ordinary world. You get refrigerator magnets. You get electric motors. You get the technology that runs your life. The quantum world and the everyday world are not separate. They're the same world, seen at different scales. I think that's beautiful. I think it's one of the most beautiful things in all of physics. That the force you feel when you pick up a magnet, that tangible pull, is quantum mechanics. It's the same quantum mechanics that people say is abstract, mathematical, impossible to visualize. No, you can hold it in your hand, you can feel it. Every time you open your refrigerator, every time you stick a note to the door, you are touching quantum mechanics. And the really remarkable thing is that we understand this now. We know why magnets work. We can calculate the exchange interaction from first principles. We can simulate magnetic materials on computers, solving the quantum equations, predicting how they'll behave. We can design new magnetic materials with properties we want. High-temperature ferromagnets. Materials that are magnetic only below a certain size. Materials whose magnetism we can switch on and off with an electric field. This is not guesswork. This is quantum mechanics applied to real materials, and it works. But there are still mysteries. We don't fully understand all the details of how domain walls move. We don't understand all the exotic magnetic phases that happen in certain materials. We don't understand how to make a room temperature superconductor, which would be a kind of perfect magnetic material. There's still work to do, still things to figure out. That's science. You understand something deeply, you can calculate it, predict it, use it. And then you find something new you can't explain. Some edge case, some strange material, some unexpected behavior. And you dig deeper, you figure it out, and the picture gets richer. But the basic story is clear. Magnets work because of quantum mechanics, because of electron spin, because of the Pauli exclusion principle, because of the exchange interaction. Your refrigerator magnet is a piece of quantum mechanics, made solid, made tangible, made something you can hold in your hand. Think about that next time you stick something to your refrigerator. Think about the billions of electrons inside that magnet, all with their spins aligned. Think about the quantum mechanical force, the exchange interaction, holding those spins parallel. Think about the domains, all pointing the same direction. And think about the fact that none of this, absolutely none of it, can be explained by classical physics. The magnet is evidence. Evidence that the universe is quantum. Evidence that classical intuition, as useful as it is for everyday life, is not the deep truth. The deep truth is stranger. The deep truth is quantum, and you're holding it in your hand.